Hey everybody, in this lesson we're going to describe the energies and positions of electrons according to the quantum mechanical model. At the same time, we're going to look at the shapes of orbitals and talk about some terms related to orbitals and electrons like principal, energy level, energy sublevel, and atomic orbital. Let's get started by just recapping some of the other more historical atomic models that you might have seen of before in a science class. Like on the far right, the earliest truly testable atomic model, that is Dalton's atom. John Dalton just said that atoms are essentially spherical little objects that cannot be broken down anymore. We later developed a different theory by J.J. Thomson called the plum pudding model, and that is probably the best representation of that is this picture over here, where we added electrons to the atom. We knew there was something positive in there to balance the charge of those electrons, although we didn't really know what that positive thing was yet. And those electrons were just random. Following that, Rutherford discovered that this positive charge, this mystery positive charge that Thomson didn't know about, was concentrated at a nucleus where the vast majority of the mass of the atom was located. He still didn't know how the electrons were organized, and then finally Niels Bohr organized those electrons into rings or bits. And this is the model of the atom that a lot of people have in their heads, and that honestly we still use today in just like common representations of atoms. And honestly, a lot of scientific purposes still use Bohr's model as well, because it actually works pretty well for a lot of things. But in this lesson we're going to see that Bohr wasn't actually totally correct for a lot of different reasons. One of the reasons you cannot put electrons in these very well-defined orbits or rings is that electrons are super teeny tiny, and as such they behave strangely. One of the ways that they behave strangely is defined by the Heisenberg uncertainty principle that says an electron's position and velocity cannot be precisely known. As soon as you try to measure one of these things, like if you tried to determine the exact speed that an electron might be traveling around its orbit, you start to lose information or affect the position of that electron. So the more you know about one, the less you know about the other. That is a very poor description of the Heisenberg uncertainty principle, but it is to say that it's almost impossible to define electrons as traveling in these rings. Another reason is called particle wave duality, which says that really tiny particles like electrons behave like particles, which they are, but also like waves, which is very strange but true. What this means is that, is an electron a small particle with a path of motion? Yes, but it is also a wave, and it is those two things at once. And if that's true, how can you put electrons as traveling in a well-defined ring? The point is you can't. So clearly there's some problems with this Bohr model that this guy, Erwin Schrödinger, came to fix. Schrödinger revised this electron organization a little bit more, and he called it the quantum mechanical model of the atom. We're not going to get into all the specifics of what Schrödinger did because he used a certain type of mathematics, quantum math, and it's just really complex. Too complex for the purposes of this video. What you really need to know about it from a chemistry standpoint is this. While you cannot say electrons travel in well-defined rings, you can keep track of their most probable locations. Where is an electron most likely to be most of the time? And that's what Schrödinger essentially did. And when you do that, you find out that electrons are not in orbits, the rings of Bohr. They're instead in these orbitals, these regions of space known as orbitals. Let's put these two theories side by side so you can really start to get a picture of how this Bohr model is different. Starting with the nucleus, which is totally unaffected here. Both of these models have protons and neutrons in the nucleus. Bohr has electrons in energy levels, right? Energy level 1, 2, 3, 4, and so on. The nice thing is that this new model, the Schrödinger model, the quantum model has the same. Electrons are also in energy levels here. The difference is how they are arranged, or the shapes, we'll call it, of sort of their motion or where they are. The Bohr model has electrons traveling in very specific rings called orbits, whereas this quantum model says the electrons appear in regions of space. And that's a good set of words to focus on here as you're figuring out what an orbital is. Regions of space where the electrons are most likely to appear. Let's step away from an atom for a second to get a better sense of what an orbital actually might be and some of this quantum math that Schrödinger did. Here is a map of a typical science classroom, and me as the teacher of that classroom, let's say that I am an electron, and I want to see what my orbital would be as the teacher who runs a class in a room that looks like this. Now when I'm teaching, I move a lot. So some of the time I might be here at the front of the room as I'm speaking to the class, but I move around a lot. So later I might be over here to write something on the board, and then I might be here to keep writing on the board, and then I might come back over here to underline something, and then I might end up back over here to keep speaking. I might spend a lot of time here at my computer to maybe conduct part of the lesson that way. And then I'm back over at the board writing stuff down. And all of these little circles that I'm putting just represent different moments in time where I am. It's possible that at some moment in time I'm here, or maybe, back amongst the students helping out, or maybe even in the far back of the room getting something out of my printer. But the point is, if I keep tracking my location, I will find that there are these regions of space. And I'm going to outline those regions of space as here and here. And within those regions, those are the spots where I am most likely to be. Those are my most probable locations. And what I have just mapped out, it would be my orbitals, right? This whole scenario was, if I was an electron, my orbital would be these two regions of space are my orbitals, and it is literally just a map of where I am most likely to be found. Electrons have the same thing, and in a couple minutes we're going to see what those orbitals might look like. Before we do that, let's get into some additional detail about the comparisons between these two models. So this is where it gets a little more specific. In the Bohr model, there was energy level 1, that first circular ring of electrons. Schrödinger has that too. He just calls it something else. Instead of energy level 1, he refers to it as the principal energy level 1. So it's not much of a change, but a change nonetheless. Principal energy level 1. And it's called principal energy level 1 because within energy level 1, Schrödinger also discovered that there are sublevels. In energy level 1, it's fairly simple. There is only one sublevel, and its name is the 1s orbital. So you still don't know what the 1s orbital looks like, but that's okay. We're going to get to that. We're just keeping track of which orbitals are in which energy levels. Bohr would say after energy level 1, there's a second bigger ring called energy level 2. Schrödinger says yes, that we're just going to call that principal energy level 2 because within that principal energy level, there's actually two different sublevels called the 2s and the 2p orbitals. Notice the pluralization on 2p orbitals. There's actually multiples of those. So in this new Schrödinger model, you'll see that there's still energy levels. They're just a lot more complex, composed of different sublevels within them. Let's keep this pattern going a little bit more. Bohr says there's energy level 3. Schrödinger says yes. Principal energy level 3, which has, go figure, 3 different sublevels. You should start to actually notice some patterns here in the quantities of sublevels. And even the types of orbitals within them, right? So there's going to be a 3s, that's one of our sublevels, 3p, and a new one this time called the 3d orbitals. We'll do this just one more time to help you spot those patterns. In energy level 4, what Schrödinger calls principal energy level 4, you guessed it, there would be 4 different sublevels, and as you can probably predict, they repeat the same ones as in the past orbital set. This time the 4s, 4p, 4d, we just add a new one each time. In the 4th energy level, it would be the 4f orbitals. The only remaining piece of information that you might want as somebody learning about orbitals is What do they look like? So that's how we're going to end this whole thing, is actually drawing out the different orbital types. So we'll start with s orbitals. Specifically, we'll draw the 1s, beginning with the nucleus of the atom represented here with this little dot. We're going to draw x and y axes coming out of that nucleus just to help orient ourselves in space. And I'll switch colors here, maybe to purple, to show the electrons. Now I'm going to do this the same way I mapped out my orbital as the teacher in a classroom. I'm just going to put a little circle every time the electron appears in a particular position. And I'm just going to sort of keep doing those, and eventually you'll start to see this orbital shape develop. Now notice the electron seems like it's most likely to appear in this region of space. Could be here, or even way over here, but there is a pattern that shows an electron in a 1s orbital is most likely to appear in a spherical region of space. I'm going to label that word spherical. That is centered around the nucleus, and that is it. That is what a 1s orbital would look like. Keep in mind, all these circles, all these dots are not multiple electrons. This is just one electron, and we're seeing its most likely location. I'm going to switch colors one more time just to address the fact that in the list we made prior to this, we listed out multiple different s's, right? There was a 1s, a 2s, a 3s, a 4s. So I want you to see the differences between those. The good news is they're not that different. In green, I'm going to map out what an electron in a 2s orbital might look like, or where it might be appearing. If you do enough of that, you'll see that a 2s is also a spherical shape. It's just a little bit bigger. I'm not going to draw the 3s orbitals, but if I did, they would be that same shape, but larger and larger the further out in energy level you go. So s orbitals are just spheres. Let's do one more drawing, starting with a nucleus, x and y axes, and this time we'll do the p orbitals. Starting with the 2p's. We're not doing 1p's because there's no such orbital as 1p. If you go back to the list we just made, you don't see p orbitals until the second energy level anyway. And let's use green to stick with my second energy level color from before. I'm going to skip all the little dots and just jump straight to the shape that these electrons would end up in. The p orbitals are a little bit more complex. They don't have a spherical shape. Instead, they appear in what are often called lobes. So an electron might spend some of its time up here above the nucleus, and then another part of its time down here below the nucleus. It could be technically in any location, but most of the time it appears within these lobe shapes. There's a little bit more detail to this that we are skipping over for the sake of time in this video. The only other thing that I'm going to add in here is that because these particular lobes lie along the vertical axis, what is usually the y-axis, what I've technically drawn is called the 2py orbitals. And that's important because if you're drawing the 2p orbitals, there's not just one set of lobes. There's a whole second set of lobes that instead would lie along the horizontal, what is usually the x-axis, called the 2px orbitals. And there's even one more region of space that we could draw in here. This one's a little bit trickier because we now have to come three-dimensionally out of the page. So it's tough to do this on a flat video surface, but this thick line represents a direction that is technically coming straight out of your computer screen at 90 degrees, and this dashed line represents going straight back behind the computer screen. If you know this from math class, I'm drawing out the z-axis, and we would also have a third 2p orbital that goes behind the screen and out in front of the screen, oriented along the z-axis. So there are three different p orbitals, the 2px, 2py, 2pz, in these lobe shapes. The d orbitals we're not going to draw because they look like this. First of all, there's 5 of them, and each one individually has 4 different lobes. You can count them here. One of them only has 2 lobes, but then it has this strange donut shape. Keep in mind, bizarre as these look, at the center of these spinning lobes is the nucleus, and these are the regions of space the electrons would be most likely to be found in. The f orbital's even more complex. There are 7 of those, and they look like this, so there's definitely no way we're going to draw them out. So these are the shapes that electrons are actually found in the most accurate version of an atom that we have today. That also wraps it up for this video. Thanks a lot for watching.